Okay. So Dimitri, thank you for this very nice overview. So in my talk, I'm going to get into more of the gory technical details. And really what I'm going to try to talk about is I'm going to try to answer these questions here. Once you have a blob and an image, how do you decide it's a planet? How do you get a nice spectrum, like all this spectra that Dimitri showed you, and somewhat like how to get nice astrometry and nice orbits from your data. So I'm not going to go over recent results. I'm going to kind of build my talk around data from the Gemini Planet Imager. So this is data around 5000 eV for 5000 eV that Dimitri talked about. All right. So what am I going to talk about? I'm going to talk about the sources of noise. I'm going to tell you what all those speckles are about. So it's going to be the first part of my talk. Then I'm going to talk about how we really actually get rid of those speckles. And then I'm going to finish with the astrophysical noise. So let's just start with the speckles and where they're coming from and what's going on with those. So this is a Gemini Planet Imager image. This is what the data looks like. And I'm going to try to kind of hand-wave my way through this image and describe to you the key characteristics of this noise. As a warning here, just look here. Display is not good enough. There's a planet in this data, but you just can't see it yet. All right, so instead of going through the full image formation theory, like chronograph propagation that Dimitri showed you, I'm just going to refer you to this really old paper that's beautiful and that really explains how astronomical image and AO image are formed. And this is a paper just about just about atmospheric turbulence. That's 1981, before AO existed, but all the theory is laid out in this paper. Okay, I'm not going to go over this. The few things you need to remember, this is pretty straightforward. Your image is the convolution of your astrophysical scene with your instrument response. We're doing long exposures here in chronography, so the instrument response is average over time. The second point is that you take this convolution. If you take the Fourier transform in your image, then instead of being a convolution, you have a product. Right. The other thing to remember is this relationship. You don't need to do any optics or anything; just take it at face value. But the instrument response is the Fourier transform. It's the square of the Fourier transform of whatever is at the entrance of the telescope or at the entrance of the chronograph. You take these 2 points, you go through a derivation, not going to go through it, and what you're finding is that what you care about is just the instrument response, because your source of noise is just the image of a star. So you don't have a complicated astrophysical scene, you just have 1 point. So you're interested in the instrument response of your system, and what you have here, which is this expression here, it's simply the spatial autocorrelation of the time average of the spatial autocorrelation of what's happening at the entrance of your telescope. If you know what's happening at the entrance of your telescope, you know it's spatial statistics, it's temporal statistics, you can predict what your image is going to look like. That's...
I think your microphone is...
Oh, okay. So how do I do that? I can figure this out. There you go, yeah. Thank you. And that's a point that Olivier Guyot made in one of his papers in 2005. You have some statistical properties for the atmosphere of a telescope. For the atmosphere, you have for the atmosphere that's above your telescope. You have a given adaptive optic system that has a given type of performance. You can sort of predict the contrast this given system will have. Now, this is the catch about this talk. And it's about sort of the adaptive optic system. If we know what the entrance of the telescope looks like, we're going to cancel it with our differential mirror, because we can't do it. So this talk is about the part of that noise that we don't know about. that we can't measure properly, or we're not fast enough to correct it. I mean, you can go into more details. So we don't really know exactly what that residual noise look like, but there are certain like broad properties that we can infer. So let's look at this noise. So it's just, it's an electrical field propagating. So there's a beam with an amplitude and a delay. You can write it as small amplitude and a small amplitude modulation and a small delay here. And so it's 1 plus a real number plus an imaginary number. And the 1 goes away. You have a magic chronograph that most of the energy is in the 1, right? That's the bulk of the energy that's in your beam. So the 1 goes away because Dimitri showed you have a magic chronograph that kills the 1. All right? So you can look at it using these diagrams. It's just some complex number. So this is the representation of the beam amplitude at the entrance of the telescope in the complex plane. The complex number here. This is some amplitude here. So that's like the kind of the fatness of your tire. And then this is the phase. This is the beam delay. You turn on your adaptive optic system. Now the phase gets a little smaller. You still have some fatness here due to the amplitude. And then you put it through the chronograph. This is around 1. After the chronograph, it's around 0. All right, this is what they look like in the complex plane. Now, what do they look like in the image? Okay, this is not working, so I'm going to skip through these. But the whole point here, what they look like in the image, they just appears as images of planets. Just look like points. Now the nice thing here, though, all of these guys, they're symmetric. If you're in the regime that you dominated by the atmosphere and with instruments that we have like right now, all these speckles are symmetric. So you could be using some symmetric trick. It's true for instruments that we have now. For future instruments, things like W1st, this is not going to happen because we're going to do some more trick with the wafer controller Dimitri told you about that doesn't make them symmetric. So that's the first point. They're symmetric. What is the temporal evolution? This is a very nice paper by Sasha Hinckley that looks at the temporal evolution of speckles in high contrast images. So you can go over this calculation with the autocorrelation of your whatever is at the entrance of your telescope. What you're finding is that in these long exposures, the characteristic scale is the exposure time of our images. In these long exposures, the atmosphere averages out, but the errors that are due to like the gravity vector of the telescope and all these things, their time scale, 10 seconds to 100 seconds. Smack on our exposure time. So those, they don't average out. And we're stuck with them. But, however, they're still pinned, there's still a cross term, and they're still pinned to the atmospheric response. So what does it look like in the image? This is the atmospheric response. This is your halo. These are just speckles that average out, and they just look like a broad halo. And these here, these blobs here, these points here, are actually corresponds to errors on the optics, on your instrument, on your telescope. And these are the ones that are really killing you. This is a different GPI data. You can see this is a different atmospheric response where we have wind in one direction, and now the halo, instead of being this nice circular Gaussian, is like goes in one direction. And this is actually a nice image from Vanessa Bailey's recent paper. This is the gain. I'm going to talk about post-processing later, but this is like how much you gain in post-processing depending on the performances of your system. And if you're really just dominated by whatever is happening in the telescope, the atmospheric conditions don't matter. You just high-pass filter this broad halo, you're done, you don't have to deal with it. And you can see here in this tail, we actually do a lot better when the atmospheric conditions are better. So there is indeed a cross term between what's happening on the telescope and what's happening with the atmosphere, and that's why these two have to work in concert. Okay, so speckles are symmetric. They have horrible time scales because we cannot play any averaging game because they're really of the order of our exposure time or or from the ground, the length of your observing sequence. I mean, your observing sequence is going to be a few hours because that's for how long the star is up. And we're just stuck with that. The wavelength dependence. So Dimitri, I think, showed you that movie. I'm just going to show it again. Or not? OK. OK, everything crashed now. I'm not going to show the movie then. So the wavelength dependence, Dimitri showed you that movie with the noise moving radially and the image of a planet not moving. So they stretch radially. And again, this is like captured in the Fourier transform. Again, go back to this paper, read those 5 pages. Don't read the full paper because it's pretty hairy, but read those 5 pages. They're very instructive. This is true for current ground-based instruments. Again, for things like W-first, once you start doing more complex things with waveforms, this is a recent paper by John Christ. If you try to, I couldn't make a movie, but if you try to track the blobs through these wavelengths, they don't stretch with wavelengths. So for the young people in this room, 10, 15 years from now, a lot of the tricks that I'm going to show you, you won't be able to use them, and we're going to have to be more clever and find other ways to do it. So they stretch with wavelengths, they're symmetric, timescales are horrible. The last thing is I'm going to just go to this bottom line here. This is a histogram of the speckled counts. They follow modified Risch statistics. It's a paper by Remy Sumer that goes through a derivation. The actual functional form of statistics we don't really care about. What we really care about is the fact that they have this fat tail. They're attached to the chronograph response, and they have a really tail at high counts. Now, this is where the planets are. So capturing, with whatever data analysis method we're using, capturing the broad bump of this distribution is not enough. Because there could be some noise here that looks like a planet. And this is something you can see when, you go to any instrument, you see these fat tails, no matter what. This is GPy data, and you can go to HST data, you can go to any instrument, to any observatory, you will see these fat tails appearing. Okay, so, my grievances is they look like planets, they follow a modified Risch distribution with a fat tail. Their second-order moments depend on angular separation, or well the chronograph work, or well the atmosphere averages out, and the timescales are really often ordered like that. That's really annoying. For all of these reasons, most of the methods we've been using, all they're trying to do is to get a bunch of realization of the noise, build an empirical model of the noise based on that, and try to remove it. There's been a few attempts at really construct a good model of the instrument or use the telemetry to retrieve it, but by and large, all the results you're seeing right now are focused on this. So Dimitri gave a nice review, so I'm going to go through his slides quickly. The first thing you can do is just take images of other sources. So you're trying to get an astrophysical signal. It's one source minus the other, assuming that this one doesn't have any astrophysical signal. So this is what happens with HST NICMOS data. It's pretty good, but you can already see the changes even if the PSF, and this is like from space. This is very stable. But there's still some little changes here, and because the contrast of the planet is very challenging, it might get tricky. You can try to play this game of differential imaging that Dimitri talked about, and there are a few other ways to get the data. I'm going to focus on data analysis method. Then once you have this, you have a big library of noise realizations, and what you're trying to do is to take your target image, take your science image, and find the linear combination of reference images that best fit this guy here. So you can put it in this cartoon form here. You just take a chunk of your image, you put it in a line vector, and you're trying to find the coefficients of the noise realization that best abstract that best fit this science image here. Okay, so the way you do it, it's a least square problem. So you can build the correlation matrix, try to invert it, and get to your coefficients here. Of course, this is something that, it's like any inverse least square problem, it's might be poorly conditioned, so you have to play a bunch of games to try to make it work the way you want. So you can actually there's different ways you can there's different geometries that you can use, how you're splitting your image, There are different ways you can choose your images in your big stack through the rotation, through the angular sequence in ADI, or through the wavelength sequence radially. There's just a bunch of knobs you can turn. You can also turn knobs on the actual matrix inversion, and there's a bunch of papers talking about that. The key thing here is, again, we're trying to do it in a least square sense. You can also go through like a more modal analysis where you just take a principal, get the principal components of your covariance matrix. You rank each principal components by the size of their contribution to the noise. These are the eigenvalues of your PCA. You just truncate and you keep the end modes that have the most noise, and then you project your image into this. So once you've done that, this is where the magic happens. You have this data that's very noisy, and you make this beautiful image of HRA79. And you realize also, I mean, this process also makes the images in color. That's beautiful. It's just amazing. So you can do it with Palomar. You can do it with GST, the same system with a bunch of telescopes. You can also, and you have, again, you have all these methods with different knobs you're turning. And this is a comparison of like 6 different pipelines and 6 different approaches to this least squares problem that kind of start trying to say, okay, this method has a better SNR and this method has a worse SNR. This was for the confirmation of AG 95086. So then, once you have your reduced data, hopefully you have something that looks more Gaussian, and you can start putting together confidence intervals in on whether or not you have a detection. So how do you go about that? Well, what we usually do is we take these annuli here and we get the standard deviation of the noise, and this is like kind of a metric of like what a false positive rate is. There's a caveat here that Dimitri published a few years ago, is that if you take the standard deviation of in an annulus that only has 3 or 4 realizations of the noise, your estimation of the noise is not, there's an error bar on your estimation of the error bar. And that error bar can be bigger than the actual error bar. So you have to count it and you have to put it in your estimation. Fortunately, Dimitri did a great job at explaining how to do it, and this is just a quick formula that you can use, and you can follow your feed pretty quickly here. So now, how do you really decide that you have a planet? So you're counting, this is your distribution of your noise. This is histogram of your noise distribution. So these are your speckles after you fit them through some least square algorithm. And this is what the signal would look like if you had planets in the data, if you have a bunch of planets in the data. This is the histogram of what it would look like if there was actually some positive data, some positive events in the data. What I've been talking to you about is this distribution here, which is a noise distribution. You apply a threshold. You're saying that anything above the threshold that has a probability of like 10 to the minus 3 of being like coming from the noise. If it's above 10 to the minus 3, then it has to be something that's of astrophysical nature. But you don't really account for how many by using the threshold, you don't really account by how many of true planets you are missing. And this is something that over the past year or two has been showing up in the high contrast imaging community, is that we've been thinking about how to account for the false positives, but also for the planets we're missing in our data. And the way you do that is by putting together these ROC curves, where here you have the false alarm rate in the x-axis, the completeness or the probability of missing a planet in the y-axis. And as you move your threshold, here, you see these two numbers changing. So if you're on this line here, the probability to a false alarm or the probability of missing a planet is the same. So that's a coin toss. That's just a terrible data analysis algorithm. That's a bad idea to do that. If you're here, on the contrary, it means there is an optimal threshold where you can perfectly discriminate what is astrophysical, what is noise. And in reality, all our algorithms are somewhere in this space here. But this is actually the right space to compare the different methods that we're using. The problem is, before I go to that and I really get into this in detail, all we're doing subtract the signal. So I told you we have all these different knobs to fit the noise. Well, when we turn these knobs, we also subtract the signal. This is an image of GPI data. This is same stretch, same everything. Here I've kept the noise alive, but there is a planet here. Here I've really killed the noise, but there's a planet here, but the photometry is completely off. So which one is which? And how do we figure it out? Well, it's kind of a mess. What's happening? Forget about the equation here. So these are my noise realizations. This is the image I want to analyze. These are my coefficients. Well, it turns out that I also have astrophysical signal in my references due to the fact that I'm using these differential methods. And so what this is doing is this astrophysical signal is getting multiplied by these coefficients, messes up my solution, and it also changes my coefficients. So it becomes a giant mess that creates all these flux losses and all these shenanigans. How do we solve it? How people have been solving it historically? You inject a negative signal, so a negative point source in your data, and then you run optimization. You run an optimization. You run a search to try to find the. So, but I mean, once you inject this, you assume that this is going to cancel this term. Once you get the model astrophysical signal that exactly corresponds to the signal that's in there, everything is going to cancel out, and you're just going to have noise and noise residuals. This is something that has been done. You can do it on the grid search. That's something that's been done by Katie Morzinski. So this is all the trials. The trials for, so it's X, Y. So it's for a planet, you get the astrometry, so X, Y, and the brightness. And you see this nice parabola here, where the minimum here is actually the value of the astrophysical signal. You can do it in more of a Bayesian sense. That's a recent paper by Mike Bottom here. And same thing, X, Y, and brightness. Now the trick when you do that is, A, you have to rerun your data analysis algorithm every time. That's what you have to do. There's a matrix inversion. It starts to be pretty expensive computationally, in particular when you do an MTMC. B, the cost function, I show you that there was a nice global minimum, there was a parabola. There's no guarantee that really, I mean, this is a nonlinear process, so yes, maybe you'll be lucky you'll get to a global minimum, maybe not. Now, when you look at low-dimensional cases like astrometry and photometry, 3 dimensions, these degeneracies are not that bad. When you look at higher dimensions cases, so when you look at data from an integral field spectrograph that Dimitri told you about, now you have 39 dimensions, and this is becoming a serious problem. So fortunately, there is actually a way to deal with it. So you can actually take any of these least square algorithms and separate the contribution of the speckles and the contribution of the signals here in a linear way, provided the signal is small. And what you can see here is I've put a planet here in this data set. You don't really see it. You turn on the crank, and sure enough, it appears here. But you can see this is the image of the planet I've injected. This is of the image of the planet after my data analysis algorithm. And this is the image of the planet after my model. My model sort of, I mean, clearly, like, the image of the planet after data analysis is doesn't look anything like what I've injected. And you see that after, my model doesn't really follow exactly what the algorithm is. This is because the planet is a little too bright, so the signal is a little too bright here, and the linear approximation doesn't really hold. I turn the knobs, and sure enough, they fit exactly on top of each other. If I put a really faint planet in my data, well, actually, if the knob is turned not too aggressive, I don't even find the planet here in this data. If I turn it to really kill the noise and find the planet, here's my planet. And again, like, the image of the planet is completely messed up. But the point is, with the linear model, you can retrieve it perfectly. So then you can invert that model and try to do some astrophysical inference. So this is what I'm showing here. I've injected some spectrum here in the data, some planet with a given spectrum in the data. I'm turning the knobs in my data analysis algorithm, and whatever knob I'm turning gets completely messy, and the spectrum is completely wrong. I'm inverting that linear model, and now it's starting to look pretty good. there is still a little bit of residuals, but now you can play around. You can try a null test. So you're putting a planet with 0 flux. So this is actually the noise level. And when you add this noise level to the result I had before, then the spectrum is retrieved perfectly. So what we've done with this model in practice is that we're back to being limited by the actual speckle noise that we've killed by a lot. And we could, like, for this example, I could turn the crank even more and kill it even more. And then I would like exactly be on top of it right here. So we've completely removed this business of killing the signal. Now, what can we do with this? Well, we can do nice spectroscopy of exoplanets. So this is the spectrum of beta big B with GPI, a paper we're writing right now. This paper was on the archive. Jason Wang, who's somewhere in the room here, really pushed this stuff, and he looked at all the beta big epochs we have with GPI, and did this careful modeling of the PSF through all the epochs. And you can see like the data in the model look pretty good. These negative lobes, they do match up pretty well. You use this to get precise astrometry for each epoch and do an orbit fit. And what's pretty striking here is the uncertainty in PA of all the other epochs, and then you turn on GPI with this method, and the uncertainties like shrink and go down very quickly. These are the residuals from the orbit fit. You start the first GPI epoch here, and we're really at the 1 millisecond astrometry that GPI was advertised for. You can also use it for planet detection. So this is work by Jean-Baptiste, who's also here in the room. This is the classical data analysis when you're turning the knobs. If you make this careful model and you invert it, you actually find more planets. This is like the discussion that, to go back to detection theory, you can talk in terms of SNR, so the SNR as per like the false positive detection, you have a modest improvement. You have a 50% improvement when you use this method. But in terms of completeness, for a given SNR, how many planets are you missing? Here you're missing tons of planets. But here you're retrieving a lot more planets. Now, that is of course a thought experiment. Probably this for one type of planets, probably these planets don't exist in the universe, as Dimitri showed us, the occurrence rate is very low. But this is I think, the right formalism to think about these algorithms and try to move forward. And then I'm going to skip the contrast curve discussion to get to the astrophysical noise. So moving forward with data analysis, by and large, we're using blind PCA. And there's a lot of room to do a lot more things. You can use correlations between telemetry and the images. You could give up in the L2 norm. I mean, we're working in the L2 norm because it's very convenient. It's really, the math turns out to be beautiful. You could use only positive modes and positive coefficients, so it's a non-negative matrix factorization. Or you could track the motion of the planets in the data, and this is the recent paper, very, very promising by Carlos Gomez that Dimitri told you about. So astrophysical noise, 5 minutes. Dimitri actually covered a bunch of what I want to talk about, so I think I'm in good shape. This is one of the first images we took with GPI. This is a multiple planetary system, but that almost made the cover of Nature until we realized that they were all stars. Of course, they're all stars. This is like a very... But the main source of astrophysical noise is background stars. So what's been done in the direct imaging community here, is you go back, you reobserve your stars, and you have this track that depends on the proper motion of the star and on the parallax of the star, and you're looking at if you're trying to figure out is your blob, is your possible companion, is it an infinitely far background star or galaxy? In that case, it's going to follow this track. If it's not infinitely far, then it's going to remain here and not going to follow the track. All right. Now, the trick with this stuff, and it's a paper Dimitri put together a few years ago, is that when you have big error bars in the astrometry, you have to wait for a while. I mean, if Dimitri hadn't waited for a while, he would have published this as a discovery. it turns out that it was actually following the background track. So how can you try to speed things up? And like this past year, we've been starting to speed these things up by trying to be a little more clever about it. But we have more information also. So this is the 51 array example. So this is the background track. So for 51 array, we had one epoch in December, one epoch in January. So very, very close to each other. And then we got another epoch about a year later. And this was, I think, the cone of possible orbits, just based on the two epochs. This was the background track. So even in the first epochs, it didn't look like it was exactly following the background track, but we weren't really sure. However, what we knew is that it wasn't detected in 2003 in a different data set. So by combining these, we could try to fit for the astrophysical noise hypothesis, where you fit the proper motion and the distance. These are the histograms. These are the blue histograms here. And you can see that even with only 1.5 epoch, we could almost rule out the zero is, so in here, zero is here in DEC, I think. You could rule out the infinitely background hypothesis. We couldn't rule out the field object hypothesis that's kind of moving in the field, but we could rule out it's a background. We didn't really publish it with this. And of course, once you add the third epoch a year later, then you can rule out. You can really and a lot of the astrophysical noise hypothesis gets tightened up, and then you can show that there's very, very few stars that have this kind of motion that could be some astrophysical noise. The other information we had the colors. Okay, these are the colors of what we think the planets look like. But in particular, those they look red. Well, guess what? A redshift galaxy look red also, so they can just be in your data and be a big source of astrophysical noise. What we had, and that was very informative, is that because we had a spectrum, we knew there was this object at methane. And so when you combine what we fit for the possible motion, if it's not physically bound, with the fact that it had methane, the probability for it to be actually astrophysical noise became smaller, like 10 to the minus 8. So we're confident in publishing this. Of course, the real proof of physical association is you have to see orbital motion and you have to see orbital curvature. Orbital motion, you could have something going straight, that's still something on the side. You have to see orbital curvature. Until you get that, you're still guessing. The game is assigning probabilities that are lower and lower, and try to clean this up. Now, age of stars, 3 minutes. Dimitri talked about them. They're really important. So you need these evolutionary track that Dimitri talked about to tie in your luminosity to the mass that we're actually reporting for these planets. So the example of Kappa Andromeda, discovery paper, it was young in a moving group based on the moving group argument. So the mass would be about 12 Jupiter masses. You have a look at the moving group hypothesis, and you look at the position of the sky and the motion of the sky, and it doesn't look, really looks convincing in terms of motion in the sky, in terms of position. It doesn't look very, very convincing. You have a look at Isochronos, and it's just, the story here is that the star itself looks really too bright to be young. And in that paper, actually, Sasha put a caveat saying, well, all of these models that we're using, it has to be somewhat of a reasonable rotator. If it's a fast rotator polon, it could be young, but it's very unlikely. Sure enough, Kappa Andromeda was looked at it with Shara. It's a polon fast rotator. So it's actually young. And this is what Dimitri said, know your star. The edge of star is one of the biggest source of noise in terms of how we're reporting our results in direct imaging. So this is like one case for one star. Fortunately, there's been a lot of work on this stuff over the past year or two. In terms of ages and age indicator, there's a bunch of Bayesian methods that have been applied by Tim Brand. He's published 2 or 3 papers, and I invite you to read them to understand what's going on there. In terms of moving group, Jonathan Gagné has been making tons of progress, and he's actually starting to use this ROC curves. So here, the positive and negative rates are belonging to a moving group and not belonging to a moving group. It's not planet versus astrophysical noise. But you can start comparing different methods, and there's a bunch of progress in this field here to clean up the astrophysical noise. And so what's interesting is the past 5 minutes in the context of this workshop of Bayesian inference and all these things, I've given you a few examples where Bayesian inference is extremely powerful for the astrophysical noise we have in direct imaging. We're not that sophisticated when it comes to our data. We're using pretty ancient methods. And this is because we know very little about your noise, and this is the point I tried to make in my first section. I think there's a lot of room to do that. And I think one of the problems, I mean, this is just my personal take here, there are just not enough smart people that are looking at these data sets. And that's just because we don't find planets. And you guys don't want to look at data that doesn't have planets. And I think once we start getting these new generation instruments, have been on Sky for a couple of years, once we start getting to a point that we understand what's going on and really dig down where the planets might be, this is going to change. Still, these are I don't know, I mean, I just show you the results for beta peak, for GPI. These are superb characterization machines. Beautiful orbits, beautiful spectra. So the planets that we find, we can characterize them really, really well. What we need to do is solve the $1 million problem. That's what Dimitri showed you. Why is our distribution from 30 to 300, or occurrence rate from 30 to 300 AUs so different from the one that's obtained with RV? That's at less than 2.5 AUs. That's something we need to solve, and that's a $1 million question for now. Once we can get short exposure times, then I'm gonna have to nix my talk, because what I told you about is about the second order moment of the noise. Correlation is all second order moment. Then you have to play with the fourth order moment. It's become a mess. I don't understand what's going on. But if we get zero noise detectors, that's something that we're gonna have to look at very carefully. And of course, JWST and WFIRST will change the story also. Thank you.
Why should they be the same?
No. I'm not. I guess my wording was. Why do I think it's a problem that the RV and the direct imaging occurrence rates are not the same? I guess I did write reconcile, right? So that's what it sounds like. What I meant is find a physical explanation about what's going on, and really, and really what I'm interested in personally is to this 30 AU, can we push it to 10 or 5 AUs with direct imaging, so we can start build more of a data set that overlaps. That's what I meant. It's not a problem, no. If there might be physical processes that explain that, yeah.
Please get involved.
And in the context of the WFIRST, one of the points I was trying to make through this talk is that there are a few key unsolved questions in terms of data analysis that we don't know about yet, that we don't know how to address them. I mean, we have a few ideas, but there's plenty of room for thinking here.
No, then thanks again, Laurent.
Thank you.